All right, we're over the hump. We're over the hump, guys. This video is really just the same as the last video, just with one new definition, or two or three, depending on how you count, and then just two example problems that are very similar to what we just did before. Okay, so yeah, take a breath. This one will be better than the last one. Maybe it won't be as interesting though, but it'll be easier. Let's start with the definition. Okay. Oh, I told myself I'd get a video ready for you guys before starting this video, but that didn't happen. So let f be continuous, non-negative, and defined on A to B. Take a moment. What are we talking about? Remember, continuous means that there's no gaps, right? So you can all draw the whole thing without picking up your pencil. So this is not a continuous function. That's a function with a discontinuity. All right, remember continuity from Calc 1. Non-negative just means not negative, positive or zero. Some interval, okay? And with a partition on A to B. We'll call this partition, again, the set of x sub I. So there's a partition. Again, partition just means slicing up the pizza. Then we have this thing that's the sum from I equals 1 to n of the function evaluated at some x sub I star times delta x. Breathe, it's okay. This is exactly what we had in the problem before, right? Look at this. Let's maybe not look at this picture, but the sum, we're adding things together. Delta x is just a width. The function evaluated at different x's is this. This is really just what we were doing before. Last time we had n equals 4. This is just the width. This is just the height. We're adding all the rectangles together. Nothing new. All right, this is called a Riemann sum for the function f. Okay. And a little disclaimer, x sub I star is any, it doesn't matter actually, any point in the interval x sub I minus 1 to x sub I. So in that partition, right? Go all the way back to that partition, x sub I star is just any point in that piece of the partition. So maybe some random pepperoni on one of those slices. All right, so then we have one more part of the definition. The area under the curve, well, it can be approximated by this, right? We just showed that in the last one, and we can approximate it. And the bigger that n is, the better the approximation. The more and more rectangles, the smaller they get, the better the approximation. Well, it turns out, under certain conditions that we've already mentioned, continuity, the non-negativity, there are ways around that. Actually, there are ways around the continuity part too, but we're not going to make things too complicated. We're not going to make things any more complicated than they already are. And the area under the curve is just the limit, as n goes to infinity, of this Riemann sum. As the partition gets finer and finer, smaller and smaller pizza pieces, as the number of rectangles gets bigger and bigger and bigger, the area under the curve is exactly equal to the area of all the rectangles. If you have infinitely many rectangles, it's not an approximation anymore. It's exactly the same. Any finite drawing is going to have error. More and more rectangles that you draw, smaller that error is going to be until it's literally zero. That's the magic of limits. The magic of limits. Oh, that's cool. All right, so that's the area under the curve. I promised we'd find the area under the curve, and by George, There it is. Probably not what you were looking for, but there it is. Don't worry, it gets better. This is only the first lecture of Calc 2. Think of how many cool places we have to go from here. It's kind of like when we start Calc 1 and we do all these limits by hand, we do the definition of the derivative by hand, and it's really messy. And then we go, oh, look at all this other cool stuff. Wow, calculus is really neat. These people were kind of smart. It's the same thing that's happening here. So Riemann sum is just adding up all the rectangles. Area under the curve is when we take that to infinity. That's kind of cool. So we got a little exploration for you guys. Let's show this off. It's kind of cool. It's somewhere here. Definitely very prepared. Look at all this stuff I'm skipping. Check this out. So there's a lot of stuff on the left. You don't have to worry about it too much. This is a spoiler right here. Don't look at this. Big spoiler. All right. And I realized that by saying that, I just drew more attention to it, like the Streisand effect. So this is the actual area under the curve of x squared between 0 and 8. The actual area is about 170 and 2/3. Now we can get an approximation for that. We have 3 rectangles. These rectangles are not left rectangles. They're not right rectangles. They're actually middle rectangles. The height is determined by how high the function is in the middle, which is usually kind of nice because then you have a bit of an over approximation and an under approximation. If we use 3 rectangles as our approximation, 166 is actually pretty close to 170. So even with 3 rectangles, that's pretty good. All right, and watch. As I play the video, the number of rectangles is going to increase. The approximation is going to get closer to the real value, and you're going to see the rectangles grow. More and more rectangles. As we add more rectangles, they have to be thinner. As the rectangles get thinner, the approximations get better. Look at those areas of all those rectangles and see that as we add more and more rectangles, the drawing of all those rectangles is almost becoming the actual area under the curve. And look at our approximation here. The approximation is getting really, really close. We're up to 160 rectangles. So many rectangles. And that's what we're doing here. Area under the curve, Riemann sums. That's what's happening. We're taking the limit as n goes to infinity. As we get, even with 190 rectangles, this is a pretty darn good approximation. And infinity is a heck of a lot bigger than 200. That's another fun fact for you. Infinity is bigger than 200. More genius facts in this math class. Okay. So anyway, let's get back to the lecture. So that's really what we're doing here. Just a bunch of rectangles, a bunch more rectangles, give better approximations of that area. Now there's some things to think about here, like limits of functions are different than limits of sums, right? Because we're really looking at the limit of a sum. And that's like a Calc 3 type thing when we get into sequences and series, because this really is a sequence. And a series is what happens when you add up a bunch of sequences or adding up a bunch of elements of a sequence, and they either converge or diverge. That limit is a little squirrely. That's Calc 3. We don't have to worry about that today. And it turns out that it really doesn't matter at all which point you choose in the interval. The subinterval doesn't even have to be the same width or something like that. Riemann sums are not the only way to construct an integral. There's something called the Lebesgue integral. I haven't even mentioned integrals yet, though. I should stop talking about integrals. 2 more like small definitions here. Very tiny definitions. We get an upper sum if our choice of x star, x sub I star, maximizes our approximation? And if it's a lower sum, right, it's going to be the same thing. Get a lower sum if our choice of x star minimizes the approximation. This is just my shorthand. The squiggles mean that this thing is the same as that thing. I just don't want to write it twice. So we've actually done some upper and lower sums. Over here in example 4, that was an upper sum. Our choice of x sub I star was the furthest to the right in this case. Over here, that was actually a lower sum. Our x sub I star was the furthest in the left of the subinterval. So we actually have already done lower and upper sums. Now, if the function's not monotonic, monotonic just means it's only going up or only going down or staying flat. If it's not monotonic, then and it's not as simple. Upper and lower are not as simple as left and right. Right? If we had something like this, then lower would start off on the left, but eventually lower would then switch to the right. It just depends on whether something's increasing or decreasing, whether we use the left or the right, if we want upper and lower. But the book's going to be pretty nice. It's not going to trick you out too much like that. So just 2 examples, and then we'll be done with this video. We're somehow already 12 minutes into it. Time flies when you're having fun, you know? Wow. All right, let's do example 5. Gosh. Find a lower sum for the function f of x equals 10 minus x squared on the interval 1 to 2 with n equals 4. All right, so we're just going to draw a picture, and it's almost exactly like the video before, but this time we have to make sure that we're only getting the lower approximations. We want the rectangles to be as short as possible in each interval. To draw a picture, we're only caring really about from 1 to 2. 10 minus x squared. We know that's a parabola that will look like this. We only care about this middle interval. If you want to get a better graph, this is just function transformations. Adding 10 moves it up. Negative means it's up, kind of upside down. When x is equal to 1, function value is equal to 9. When x is equal to 2, the function value is equal to 6. You can figure this out. All right. Okay, so we need the lower sum. So we need to split this up into 4 rectangles. And in every interval, we need the smallest, the shortest rectangle possible. So in this case, shortest rectangle is going to be when it's on the right. And because this function is only decreasing, the function's only going down, it's actually always going to be on the right. If it was switching between going up and going down, then some of them would be on the right, some of them would be on the left. Remember, lower sum just means that all of these rectangles have to be under the graph. You draw anything and you have something going over the graph, it's not a lower sum anymore. So now we just do what we've done before. It's just the area of all of them up. Add them up together. Each one has a width of 1/4. Right? Dividing it into 4 pieces. The whole piece is 1. You got 1 and you're dividing it into 4. Well, each one's 1/4. And now we just add up the function value at each of these. So where's this guy going to be? Well, that's just the function value at 1 1/4. What's this guy? Function value at 1 1/2. What's this guy? Function value at 1 3/4. And the last one's function value at 2. That's it. To keep things a little shorter, I'm not going to plug this into a calculator. You can do it no problem. Be very careful with parentheses here. All right. You're all capable of plugging numbers in a function, so feel free to pause the video and finish that if you'd like, or we can go on together. Last example of this video, example 6. Find the upper sum for y equals sine x, ooh, some trigonometry, on the interval 0 to pi over 2 with n equals 6. So things are going to get more interesting here. We're still going to start with the picture. You can use Desmos to help you if you need some help on here. Remember how sine goes. Sine starts in the middle, kind of oscillates like that. Where's pi over 2? Well, the period's 2 pi, so this is 2 pi over here. Means this is 1 pi, which means this is pi over 2. So pi over 2, 0 to pi over 2 is just the part of this that is increasing. So I'm just going to do this. And again, it goes down. But this is pi over 2 right here. Starts at 0. Pi over 2 is going to be when it's at its maximum, which you can also remember from the unit circle. We need to divide this into 6 pieces. So we can divide it into half, and then divide each half into thirds. Half of pi over 2 is pi over 4. And then divide that into thirds. Maybe or maybe not can do that. But this first one, that's just going to be a third of pi over 4. Pi over 12. Well, they all have the same length. So this will be 2 pi over 12, which is pi over 6. That's 3 pi over 12. 4 pi over 12. 5 pi over 12. And 6 pi over 12. And we need the upper sum. So for this first rectangle, do we draw it on the left or the right? We need an upper sum. It's going to be on the right because the function's bigger on the right. Now for this rectangle, left or right, same reason. Bigger on the right, and we need an upper sum, so we're going to do it on the right. Do it on the right because it's bigger on the right. Do it on the right because it's bigger on the right. Do it on the right because it's bigger on the right. And do it on the right because it's biggest on the right. And now we just set this up the same way as before. You're going to have to remember your trig. This one you'll probably want a decimal approximation for. You can always ask me whether I need an exact answer or a decimal approximation. But our approximation, in this case, by the way, is the same as R6. Upper and lower is not always the same as right and left. But here the function is only increasing, so an upper sum is the same as right rectangles. So each one has a width of pi over 12. You can write pi over 12 plus the height. Sorry. You can write pi over 12 times the height plus pi over 12 times another height. But it's easiest to just factor out that pi over 12 since they all have the same width. All right, and the first one is just going to be the function value right here at pi over 12. Plus the second one is going to be the function value. The height is just the function value. And that height is the function value at pi over 6. And so on. Function value at pi over 4. Function value pi over 3. Function value at 5 pi over 12. And the function value at pi over 2. You can just add all of those up. Plug them into the function. You can do some of these by hand. Actually, technically, you can do all of them by hand, but some of them will require the half angle formula or the angle subtraction formula, which we won't need to go into. You can use a calculator and get an approximate answer here. And that's all there is for this video. Cool. You want some more practice? Check out the selected homeworks problems video. I've got one more video of applications, which really is nothing new. And in fact, the book doesn't even have a specific section for applications. I just wanted to make one so you can get some explanations on where some cool things are coming from. And this next one is going to be the best in my ratings of videos. But I can't actually rate all the videos and rate all the sections, because you never want your professor to say this is the worst one, which I think I've already done. Well, good luck. Hope you enjoy some homework problems, and bye bye.